Alright, tonight we're going to finish up section 1.2 and we're going to talk a little bit about function notation. Okay, when we talk about function notation, we're talking about this symbolism right here, the f with the x in parentheses. Now that's not a multiplication. We actually read that as f of x, or we could call that the value of the function at the number x. Whether the function is denoted with f of x, it could be g of x, it could be h of x, it could be just about anything. Okay? Keeping in mind that the value of x is the input, and then the f of x represents the output. Those are our domain and range values. So x is still the domain, but now instead of saying that our y values are our outputs, we're saying that f of x, the value of the function at some specific value of x. So if we're going to evaluate a function, we've got this function f of x equals 2x squared minus 3x plus 4. And we want to evaluate that when x equals negative 2. So it's just like evaluating expressions that you did back in Algebra 1. Wherever there's an x, you're going to replace it with a negative 2. So f of negative 2, because our x is now negative 2, equals 2 times negative 2 squared minus 3 times negative 2 plus 4. And it's all just simplifying. So we start evaluating. That's going to be 2 times 4. Negative 3 times negative 2 is plus 6 plus 4. So we've got 8 plus 6, which is 14, plus 4, which is 18. So that means f of negative 2, the value of the function f when the x is negative 2 is going to be 18. Okay? So if we were thinking in terms of ordered pairs, we would have the ordered pair negative 2 for my input and 18 for my output. That would be my point on the graph. Okay? So let's look at another one. Let's evaluate for f of x plus 3. The process doesn't change. We're going to take our original function of f of x equals 2x squared minus 3x plus 4, and we're going to evaluate that for f of x plus 3. And all that means is wherever there's an x, we're going to replace it with x plus 3. So it's 2, take out the x, replace it with x plus 3, and then it's squared. Minus 3, replace x with x plus 3, and plus 4. And now it becomes just a matter of simplifying everything. So x plus 3 squared is x squared plus 6x plus 9. That's going to be minus 3x minus 9 and plus 4. So continuing on, we've got to distribute the 2. 2x squared, 12x plus 18. Everything else is just going to kind of carry along for now. And we need to combine like terms. So the value of the function f when I evaluate for x plus 3 is going to be 2x squared. I've got 12 and minus 3 for x's, so that's going to give me a plus 9x. I've got 18 minus 9, which is 9, plus 4 gives me a plus 13. So here is the value of f evaluated for x plus 3. Okay? When we talk about graphing, okay, in the past you've thought of ordered pairs as being x and y. Okay? But when we're graphing functions, the y changes its look a little bit. So instead of plotting the points x and y, as we saw in that part A of the first example, we're plotting the value of x and f of x, the input and the output. The input is the x, the y-axis really becomes the f of x axis, the axis that represents the function. Okay? And when we look at graphs, we have what's called the vertical line test. Okay? The vertical line test is something we can use when looking at a graph to determine if the graph represents a function. Okay? And what the vertical line test says is that no vertical line may intersect the graph more than once. So no vertical line can intersect a graph more than once in order for that graph to be a function. If you can find any vertical line that crosses the graph twice, that graph does not represent a function. So let's look at a couple of just sketches of some graphs. Okay, there's one. And here's another one. Okay. So if we look at the graph in A, does that graph represent a function? Okay. And the answer is no. This is not a function, because I could pick out several vertical lines that are going to intersect the graph in two different places. If the vertical line crosses it more than once, not a function. Whereas the graph in part B is a function, because no matter where I would draw my vertical lines, I'm never going to hit that graph, that blue line, more than once. Okay? So B represents a function, and that's actually what we call a linear function. It's a straight line. Okay, let's check out another one. Okay. If we look at this graph here, this is our x-axis, this would be our f of x-axis, okay, and here is our function f. Does that graph represent a function? And the answer is yes. This is the graph of a function, because no matter where I would draw a vertical line, I'm never going to hit that graph more than once. Okay? So that does represent the graph of a function. Let's call this x and g of x this time. Okay? And let's graph this. Okay? So does the graph of g represent a function? And the answer is no. There's a vertical line, hits it twice. So I shouldn't call that g of x anymore, because I now know that this is not a function. Okay? It still represents some relation, it still represents some groups of ordered pairs, but it does not represent an actual function. So when we look at graphs, there are certain things that we can determine, or that information that we can get from graphs. Okay. So one of the things we can look at is whenever there is a closed dot. Okay. A closed dot tells us that the graph stops at that point. Okay. The graph stops at that point, and the end point, which is what it would be if that's where it stops, belongs to the graph. Okay. That endpoint is one of the values on the graph. It is a solution to that particular function. Okay. Whereas if we were to have an open dot, okay, an open dot is still going to be an endpoint, but it does not belong to the graph. Okay. So just like you did back with inequalities way back in Algebra 1, you might have a graph that is on a closed interval. It only goes from one value to another. If there are closed dots on the endpoints, then those points are included. They are part of the graph. If there are open dots, then those points, even though the graph stops, those points at the open dots are not included. They are not part of the graph itself. It's just showing you that it's going up to there, but not quite reaching it. And the last one is if our graph has arrows. And what the arrow indicates is that that graph extends to infinity. Okay? And what do we mean by that? We mean that it goes on forever. Okay? It never stops. Okay, so like we saw in some of those graphs back there, like this one here, we got a parabola, and we put arrows on it. The arrows indicate that that graph is going to keep going in the upward direction on each side indefinitely. It's just going to keep growing and getting bigger and bigger and bigger. Okay? All right, so if we were to look at a graph, okay, let's say we have this graph here. This graph has endpoints. Those are supposed to be closed dots. I'm doing the best I can here. Okay. Where those values come down to the x-axis, okay, these values in here, notice I'm using brackets because they're going to be included values. Okay. Those values are going to represent the domain. Whereas the values that come over towards the y-axis, okay, and that would be the lowest value at this point here. The highest value is coming across the top up here. Okay, should have got that a little bit closer, I guess. Just can't quite hit that right on that line, can I? Yeah, you get the idea. These values, okay, represent our range. Okay, so we can also determine domains and range of graphs by functions by looking at the graph, seeing which x values are being covered, which y values are being covered by a particular graph. Okay. So let's look at kind of a more specific example here. Let's say here's -4 on the x, here's +4 on the x, okay. Here's 4 on the y. Spacing's not quite evened out there very well, is it? So we'll bring this in here, we'll call that 4. Okay. And let's say we have this graph. Starts here, goes up, and it comes back down over here. Okay. Our domain is going to be the set of x's such that -4 is less than or equal to x is less than or equal to 4, using the set notation. The values of x that are being covered by that green curve start at -4 and they end at +4. The range values, if we make this point over here 4, 1, okay, and this point over here, let's say that's 4, 1/2, our range is the y values that are going from 1/2 is the smallest, less than or equal to y, and 4 is the biggest.
Yeah.
Okay? So from here up to here, okay, this represents our range from 1/2 up to +4. Mention here is when we talk about zeros of a function. This is going to be a big deal. This is something that we are going to use a lot. The zeros of the function, okay, are the x values where f of x, where the value of the function is equal to 0. Okay? Therefore, these little 3 dots in this little triangle, that's a mathematical symbol that we use, that stands for the word therefore. Okay? Therefore, real zeros are really the x-intercepts of the graph. Okay? So this is something that we're going to use a lot throughout the semester, and this is something that we'll talk about more in class tomorrow. Okay, so when we come to class, we'll try to clear up any of this. I know some of this stuff is a little bit confusing, and we'll talk a little bit more about zeros, and that's something that's going to carry on all semester. Okay, so we'll see you then.